After understanding the three mathematical basic principles, we are finally ready to demystify polarization. So let's begin. If I shot an unpolarized light towards your eye, you would see something like this. All the electric field vectors, crazy and randomly oriented, undisciplined, passing through your eyes. And I would depict it by using a green dot to show the light coming out of the monitor and a bunch of arrow marks as discussed in the earlier episode. But you know what? Dealing with this unpolarized light is not so easy. So what we're going to do is, we're going to take an electric field vector and decompose them into two perpendicular directions. Say these two perpendicular directions. Wait, what? You're going to take each and every electric field vector and decompose them into two perpendicular directions? Yes. There are infinite of them. So what? I'm not afraid of infinities, but they're all crazy and randomly oriented. But that's the key! The key is that they are randomly oriented, so we can use statistics. The statistics tells me if I decompose each and every electric field vectors into these two perpendicular directions, then the intensity of the light must be equally divided among the two directions. Why? Because it's randomly oriented. What I'm trying to tell you is, if the original intensity of the light is I0, then after decomposing them into two perpendicular directions, each of them must have an intensity of I0 by 2. This is just like tossing a coin and having 50-50% probability of having a heads or having a tails. Therefore, even if an actual unpolarized light contains electric field vectors randomly oriented in all the possible directions, it is mathematically equivalent to think of them as a wave containing electric field vectors vibrating in only two perpendicular planes having equal intensities. Did you get that? And there's nothing special about these two perpendicular directions. There's nothing special about horizontal and vertical. I just chose them randomly. I could have also chosen these two perpendicular directions and I would get the same answer. I0 by 2 and I0 by 2. You can choose any two perpendicular directions to model your unpolarized light and they would all be equivalent to each other. Now let me summon a polarizing filter. Ooh, nice. So what does a polarizing filter consist of? At the most basic level, a filter can be thought of as made up of vertical wires all parallelly aligned to each other as shown. If you now shoot a vertical electric field vector, then this is going to make the electrons in the wire oscillate. Thus the electric field energy gets converted into the kinetic energy of the electrons, which is finally dissipated as heat. Thus, the vertical electric field vector is absorbed. However, if a horizontal electric field vector is shot on the Polaroid, then it will try to make the electrons oscillate in the horizontal directions, but the electrons cannot oscillate in the horizontal directions, and therefore the electric field energy is not absorbed, and this electric field vector can pass through. So you see what's happening? One component of the E field has been absorbed, the vertical one, and the other component passes through. So in other words, this acts like a polarizer. So if we now kept this in a path of an unpolarized light, and if we use the mathematical equivalent model, then you would see that our light is now linearly polarized. Woo! But now I'm going to ask you a question which I want you to think and try and answer. If the incoming light has the intensity I0, what do you think will be the intensity of the outgoing polarized light? Come on, you can think about this. Pause the video for a while and think about this. Now seriously, think about it. Now if you thought that the intensity of the original light was divided among the two perpendicular directions equally, I0 by 2 and I0 by 2, and since one of them got absorbed, the vertical one, and only one went through, the horizontal one, only I0 by 2 survived, then you are absolutely right. The outgoing polarized light now contains intensity I0 by 2. So now we can understand the first rule of polarization. If an unpolarized light gets polarized, then the intensity reduces to half. And I'm going to call this as the 1/2 law. Since the filter only allowed electric field vibrations in the horizontal, we would now say horizontal direction is the pass axis. And therefore, for any filter, the pass axis is always perpendicular to the wireframes. What would happen if I rotate the filter counterclockwise, making the pass axis 45 degrees with the horizontal? Well, now I can rotate my mathematically equivalent model also by 45 degrees counterclockwise, because remember, when we decompose the electric field vectors, I told you we could have chosen any two perpendicular directions to decompose it. And now again I would find that there would be electric field vectors parallel to the pass axis that will pass through, and electric field vectors perpendicular to the pass axis that will be absorbed. And again, I would see I0 by 2 intensity coming out of it. Therefore, now the light would be plane polarized at a 45 degrees angle with the horizontal. And I could rotate the filter further 45 degrees counterclockwise, and now the outgoing light would be vertically polarized. Again, having the intensity I0 by 2. So what this tells you is that the intensity of light is not affected by rotating the filter. By rotating the filter, all you're doing is changing the direction of the outcoming polarized light, but it has no effect on the intensity. The intensity always remains I0 by 2. Does it go against something we saw in the beginning of the first episode? I can prove this to you. Here is the unpolarized light from the original experiment. And now here is the same filter I used before. When I keep in front of it, I see the intensity decreasing. Now the camera may not be able to pick it up properly, but I can promise you that the intensity has decreased. Okay, so I0 intensity, unpolarized, and now it is polarized, I0 by 2. And now I'm going to rotate the filter and you would see nothing happening. The intensity remains exactly the same, I0 by 2. However, what does happen, which you and I cannot see directly, is that the electric field vectors are now rotating. Now all the electric field vectors are vertical. Now all the electric field vectors are horizontal. Now all the electric field vectors are 45 degrees to the horizontal. Let's investigate this Polaroid filter more. I clearly don't see any vertical wires in it, are there? There are. These are all microscopic wires. And they're not wires, but they are Kerapathite crystals. It's named after a toxicologist called William Bird Kerapathite. Obviously, it's a very funny story. Turns out in around 1829, one of his assistants, and get this, fed a compound called as quinine, which they used to use to cure malaria during that time, and iodine to a dog, and then looked at its urine sample and found some weird green crystals, which when Kerapath looked under a microscope, found out it could polarize light, and hence he called it Kerapathite crystals. Weird. However, he was never ever successful in creating a single crystal large enough to make a Polaroid filter. It was only after about 80 years a man named Edwin H. Lamb was finally successful in creating the first Kerapathite Polaroid filters, or in other words, dog piss filter. Ew. But fortunately, this is not a dog piss filter, because during World War II, many of the soldiers were actually infected with malaria and quinine was used to cure them. And so he had to come up with an alternative. And he found out that if you took polyvinyl alcohol and doped it with iodine and then stretched it enough, it could also polarize light. And more importantly, it was a much better Polaroid than a dog piss filter. And he called it as the H Polaroid. This is the same H Polaroid. Alright. Now comes a bigger question. What if you have an already polarized light and you incident it on another polarizer? So here's the setup. What if you have a polarizer which has a horizontal pass axis and you incident on it a polarized light having electric field vectors making an angle, say, theta? What do you think will happen? What will be the outgoing light? And I will give you three options. First option, the polarizer will say, sorry man, you can only vibrate in the horizontal direction, so I cannot allow you to go through, and hence all the electric field vector gets absorbed, so nothing passes through. B, the electrons can only vibrate in the vertical directions, so the electrons will say, sorry man, you cannot make me oscillate, and therefore the entire electric field vector passes through, and nothing happens. C, somehow the outgoing light is now polarized in the horizontal direction. Which one do you think it's going to be? To answer this question, we are going to use vector analysis from our previous episode. Remember that this electric field vector, if it has an amplitude E0, it does have a component along the path axis E0 cos theta. And therefore E0 cos theta gets through. And hence the answer is C, because now the light is polarized in the horizontal direction. But hey, wait, what happens to intensity? Remember from the previous episode, intensity is proportional to the amplitude square. So I0 must be proportional to E0 squared. And therefore, the outgoing light must have an intensity I, which is proportional to the E0 square cos square theta. And thus, the outgoing intensity becomes the incoming intensity I0 times cos squared theta. And this is what I call as the cos squared law. This is the famous Malus law of polarization. Okay, with the two laws ready and a couple of more minutes of attention, we are finally ready to crack our initial problem. Here's the setup. I have an unpolarized light source, I0, and two filters, both having their path axes aligned horizontally. Let's figure out the intensity of light as it emerges out. As it passes through the first filter, unpolarized light gets polarized. We use the 1/2 law, giving you light of I0 by 2. Horizontally polarized. It hits the second filter, which we usually call as the analyzer, and since its path axis is also horizontal, all the light passes through. But if I rotate the analyzer by 45 degrees counterclockwise, now the outgoing light will have an intensity I0 by 2 cos squared 45, making it I0 by 4. Hence the light intensity reduces. And if I rotate the analyzer further 45 degrees, making it vertical, now the two filters are cross-polarized and nothing gets through. You will get 0. So now you see, as I rotate the analyzer, the light intensity changes. In the original experiment, there were actually two filters. I had already kept an analyzer right below the camera even before beginning the experiment. Please don't unsubscribe. I can demonstrate this to you. Here's the original light source, unpolarized light source, call that as I0. And here's the filter. I keep that filter in front of this. So now the light has become polarized and it is in the horizontal direction. I bring in a second filter now. This is the second filter, and I keep it this way. Almost all the light passes through. But now as I start rotating it, you can clearly see the light intensity starts decreasing, and ultimately when I've cross-polarized it, I have killed almost there it is. I almost killed all the light. So I have cross-polarized it. So there was a second filter all along which you didn't know about. Lastly, what happened when I brought in another filter in that video? It was actually the third filter, and I positioned it right in between the polarizer and the analyzer, kept in front of the camera. So here's what happens. So you repeat the calculation. I0, I0 by 2, I0 by 2 cos squared 45, which is I0 by 4, and again I0 by 4 cos squared 45, giving you I0 by 8. So the moment I introduce the third filter, the light is no longer being completely absorbed by the analyzer, because the analyzer is no longer cross-polarized. So by introducing the third filter, I have not created light. All I have made sure is that they are no longer cross-polarized, so some of the light went through. Pretty cool stuff, isn't it? So finally the mystery is solved thanks to Malus laws and a little bit of maths. But wait, there's still more to come. Does polarization have any day-to-day application? For example, why are these expensive glasses Polaroids? Do you know that these Polaroid glasses help fishermen a lot? Also, do you know that pilots are always advised not to use Polaroid glasses? Some of the camera filters are polaroids. Some animals can see the direction of polarization. Why? How does that help animals? And above all, how does 3D television work? I will do the 3D in the next episode, so stay tuned. Hey, also, if you like science and you're preparing for, say, AP Physics, or if you are a CBSE student, you should definitely subscribe.